Yeah, so hi everybody. My name is Per. I work in the core libraries team at Oracle.
My name is Klaus. I work in the performance team. So we're both doing work at JPG or at Oracle, Java Platform Group. Thanks.
Yeah, and we are performance enthusiasts, both of us. And this is not going to be like a regular presentation. It's going to be more like a discussion. So we're going to discuss here, and we invite you to participate. Maybe we can take most of the questions at the end. But it's not like we're going to stand. That's why we're not standing at the podium. OK, so let's start.
Right. So we started collaborating like a year ago with some articles about recent performance improvements, like every 6-month release of Java JDK. Something we've been planning for a while, but finally got the time to do.
Materialized.
Materialized, yeah. So we want to continue that. If people seem to be appreciative of digging deep, or also showcasing like the smorgasbord of changes coming into each and every other release.
Yeah, and it's in so many different areas, so it's good to have this kind of gather all the
like an eagle eye view of things going on.
Yeah, and then we have for 25 as well.
Yeah.
So hopefully we'll get it for 26 one of these days.
Right.
So we worked we put a lot of effort into improving the performance of the JDK. And here is an example where we run this spec 2015 jobs. On the left-hand side here, you can see a job that's called critical job JOps, and that is geared towards something called latency, which we're going to talk about later what that actually is.
Right.
And on the right-hand side, it's more of throughput, which we're also going to talk about later on. But the good thing is that latency comes down a lot without even, you don't even have to recompile your code. You will get like 10% score improvements by just changing JDK.
All right, and this is from 21 to 25.
This is from 21, yeah, from 25.
So just by the few, two most recent LTS releases. Mm. And if we look back even further, the improvements are even more
massive. I would say
massive, yeah.
Yeah, and it should be noted that every tiny percentage here is a struggle because it's already so optimized. So we are really happy to see these figures materializing here.
Right. Every incremental improvement going forward is probably going to be, a lot of more work, but we're not going to be intimidated or dissuaded by that.
Exactly. And here is another example for a more modern framework, which maybe use some modern constructs of Java, and then the difference is even.
We're Oracle, so we have to show Helidon, of course, but the same thing kind of applies if you look at other Quarkus or Micronaut, whatnot.
Exactly.
The difference there, if you'd characterize a little bit, is like spec 15 is an old benchmark, doesn't use lambdas, doesn't use much outside of fork yarn pool. If you use a more modern application as your benchmark, you will see
an even more pronounced difference.
More work going on in modern language features.
Yeah, I'm just curious, how many of you have any project still running on 8 or earlier? Okay, so you have some work to do here.
A few hands, not too many.
No, actually, I was surprised. I was expecting more. Maybe they wouldn't admit to it.
Right. How many is running on 17 or 21? One of the more hands, lots more hands. Thanks.
Yeah. Okay.
How many have already upgraded to 25?
Good.
More than 8.
More than expected.
More than 8.
That's great. Okay, so we're going to talk about metrics today. I mean, performance is a very wide, concept. So we're going to speak a little bit about about different metrics there, and some challenges when you are measuring performance. And then we're going to zoom into more details. How can we get this kind of performance? How can the JIT or the C2 compiler help us? And then we're not going to talk about 13 performance improvements. We will see how far we will get because we want to discuss some of them, and maybe we got stuck on one, or maybe we have more time and it will be more.
Yeah.
So don't expect 13. Spoiler alert. And then we're going to summarize what we spoke about. So I'm going to start talking about metrics here, and most of them are time-based metrics. So we have the usual, when we talk about performance loosely, we commonly mean average throughput. That is, how many operations per second can we actually, perform?
It's the easy thing to measure, and that many benchmarks do
Yeah,
measure.
you're just trying to squeeze as much as possible through and see what happens.
Batch style kind of benchmarks.
Exactly,
Yeah.
exactly. But then there is also latency, and that is very important in some applications like trading, and you have an SLA saying that almost all of my calls will complete in this or that time. So, for example, we talk about typical latency, and suppose you do 10,000 experiments and measure how long time will this method take, and then you order them in order, and then you look at the second last one. No, I mean, you look at the one in the middle. That's the typical one. Mm-hmm. But I went too far. I went to do the other point here, and that is if we want to talk about the 99.99, commonly referred to as 4 nines, then you have to do like 10,000, and then you just don't look at the outlier on the most right-hand side, but the second slowest one. And of course, in reality, you can't do just 10,000. You have to do millions to get any statistical significance, of course. But that's the concept of latency. And then we have startup time. And startup time is the time it takes from you start your application until it produces its first output. In the simplest example, it's like you hit return and then it prints hello world. But in a more real world example, it's when you deploy your web application or start your web server until you can first service the first incoming request. And then it's warm-up time. That's something different. Of course, the warm-up time is longer than the startup time by definition, but it's like how long?
Yeah, like time to performance, or like how long does it take for your application to warm up to the steady state peak performance?
Yeah, as you might know, Java compiles your application on demand.
Right, so it's kind of like application defined. You have to.
So this is a more loose thing.
Right. We try to pin it down in a few cases that we are measuring, but it's an elusive concept.
Maybe you can say that it's the time it takes to reach 99% of the, steady state performance or something like that.
Yeah. You have to cut it off somewhere, otherwise you just goes into infinity.
Exactly, and then there are different metrics. What do we have to consume in order to fulfill all of these requirements? So we have memory usage, of course. Maybe you have a sorting algorithm, which is faster than another, but using more memory. Well, that's not good. You have access pattern. That actually turns out to be a resource. How you access memory, if you just have a scatter loading, that's a pain. Whereas if you can address your memory in consecutive, that's much better for modern CPUs.
Like replace all your linked lists with array lists.
Yeah,
everything improves.
Or if you do matrix multiplication, do that in small tiles rather than just iterate over the entire thing.
Right.
And memory pressure is another one. If you allocate a lot of memory, of course you have to recuperate that memory via the garbage collector, and you create this memory pressure. So maybe you can do in another way that doesn't create all these objects. Mm-hmm. Or maybe you can make sure that the compiler can remove those creation of those objects.
That's great when the JIT can, constant fold and all that.
And escape analysis.
Scalarize your object so that your allocations actually disappear in practice.
Exactly. And then with thread uses, of course, if you just use one thread to do the same work, or if you use the same job with 16 threads or whatever, it's better that you conserve threads because that's a resource. Contention is another one. If you have a place in your code that only one thread can be in at the same time, that creates contention, and that's bad. So maybe you can design around that and allow some other kind of access mechanism.
Right. And most of these things you can actually get a tab on with tools these days. Like if you're running on Linux, running perf tools. You can get metrics on your app, like how many cache misses, how much contention, how much interconnect traffic is there, and whatnot. So it's like we're living in a time where all these metrics are readily available without much further ado. So that's fine.
Branch misses and all that stuff, important. Code size is another. You can write an algorithm that is maybe a bit faster. Oh, this is 5% faster, but maybe it was like 500% more code. And code space is also a valuable resource. Yeah. We only have so much place in the code cache.
It all adds up quickly. Yeah.
And then there is SIMD. SIMD is like those single instruction, multiple data, the vector operations, you can say. And that is also a scarce resource because in some CPUs they are shared, in some other CPUs the CPU needs to clock down if you use the wider versions of them, and so that becomes a resource as well. So all this boils down to energy efficiency, and I mean in today's world when energy and other resources are scarce, it's important to be able to be as efficient as possible.
Yeah, and we recently ran some numbers on this is from one of the Da Capo benchmarks that uses Spring Boot and collecting some stats just with the perf energy package and energy RAM, and we can see, you know, when contrasting JDK 8 through 21 and 25. That the energy use on like a fixed load is down 24%, and much of that is the lower one is the RAM, the memory access contribution to energy is also down by almost 40% by, you know, smarter improvements to garbage collectors, better improvements to escape analysis, getting rid of memory accesses across the board. So you know.
And you can see how this correlates with the figures we had in the beginning. Yeah. So, I mean, energy often translates to performance.
Right.
So and that's a correlation.
On the same hardware, it's like... Yeah.
What's this JDK 8 perf?
Oh, that's a commercial offering that Oracle does, right? So it's like most of the VM changes backported into JDK 8 compatible package. So if you're...
It's for those lazy people who didn't convert to Java.
Like if you're stuck on 8 and want some of the performance improvement, we have a solution for you.
Okay. Okay, platform is also important, of course. What kind of CPU we're running on, even what stepping it is. The compute to retrieve ratio has changed a lot over time. When I started using Java back in 1.0, the ratio was about 1 to 1. So it took, you know, 1 clock cycle to access memory and 1 clock cycle to compute something, whereas today it will set you back around 100 clock cycles just to get in 64 bits of memory. So therefore, it kind of pushes solutions from, you know, just caching simple things. It's better to just calculate them locally if it's very simple to do. So that, you know, changes the algorithms that we use. Number of cores is another one. Of course, if you run on a 2 CPU solution, or if you have a massive 128 platform, the program is going to behave differently.
Very much, yeah.
And these cores are interconnected in different ways. Maybe if they are adjacent on the die, they might even share caches, and so you can communicate very rapidly between them. Whereas if they're on completely different dies.
Yeah, like a NUMA setup with multiple sockets.
Yeah, I think we're going to see that in an example in 30 slides ahead.
Right,
something that has NUMA.
But you know, it's one of those research problems that, you know, even though we do as much as we can to make the JVM work nicely on multiple sockets, it's still going to be, you know, you have shared resources, you have compiler, you have compiled caches that, you know, there are modes that allows us to replicate across NUMA nodes, but it's generally recommended to, you know, run JVMs pinned to a specific node.
And maybe use other means of communication between
those. Yeah, I mean,
those.
we're working on making the JVM smarter on cross-socket deployments, but it's a very hard problem.
Indeed. Okay, operating system, of course, is important. Okay, the application is also important. How is your workload distributed? What's the shape of your data? Pollution is something that is being used often within the JDK community. It's like you run on some kind of data that has some kind of statistical behavior, and suddenly there's another behavior because you have compiled. Assuming those statistics will hold, you will get bad performance, and that's called pollution. So summing this up, we usually measure average throughput. That's our main objective. We measure after warm-up with the kind of mantra, if they compile, it's hardly used anyway. And that's the truth with a kind of a modification, because it is important at startup when you're running in compile mode. But we focus on things that's been called many times.
Right, and you know, there's a lot of fuss about AOT modes in Java, and even in those cases, you have to make sure that you don't spend too much time compiling things that aren't actually going to be run, because that adds footprint to your binaries and whatnot. So it's very important also in those cases to see filter out the things that are not used.
The garbage collector might also affect how our program behaves, of course. We have different platforms, Linux, Macs, Windows, and we will not forget our porting friends that are constantly keeping Java vibrant and possible to run on other platforms as well.
Right.
Yeah, and I think Mac OS x64 is kind of sunsetting now, so maybe we can...
Yeah.
At least I'm not looking so much at that at the moment.
We still support it for the time being,
Yeah.
but it's
But it's not our main focus.
Is going out.
Yeah.
So when benchmarking or doing performance work, measuring performance has a lot of pitfalls. One of the old sayings is don't use your laptop. Laptops tend to overheat, get warm, changes your benchmarks numbers that you retrieve. Still, we do we do a lot of benchmarking on our laptop. So,
but you have to know the limits of it.
You have to know when your system, if it how it behaves, when you can trust and not trust, run things back to back and back again, so that you see that the numbers are consistent. And if the hardware is starting to act up, have at it. But like we have a lab set up, both quite unrealistic with everything from turbo boost and hyperthreads turned off just to lock things down as much as possible.
To get it reproducible.
Yeah, for the things like we want to see every little incremental contribution from every little patch. To be able to isolate changes, and then more like setups in our own local cloud, things to measure in more the kind of system that you would run your production workloads in.
Yes.
When benchmarking, you need to make sure that you're looking at something that is comparative, that is consistent across runs. So you need to warm up, run millions of times. You need to set up your benchmark to realize that, or to guard against the fact that the AVM can do a lot of dynamic things, like figuring out that in your particular benchmark this method isn't even used, so just
throw it away.
Yeah. Dead code elimination, it's called. So the JVM does a lot of things.
It's good at speculating.
It's good at speculating.
Just like us.
Oh yeah, that's how half our work is speculating about what the JVM will do and then testing it, and then figuring out why we were wrong. and then looking scientifically at things, you run into these things all the time. If you get a benchmark from a customer, then they say that this isn't working, or this is working poorly, or whatever. So yeah, and of course when measuring time, there are lots of pitfalls. Like typically people say you use system nanotime because it's monotonically increasing compared to current time millis and such things. But you should also be cautioned that system nanotime can cause cross-socket contention.
Yes.
It needs to be synced across cores and whatnot, so it can actually pack quite a punch when it comes to contention and latency overheads. So also you should have a system that uses like these time functions sparingly or in a controlled fashion, so that you amortize the cost of them over time.
Yes.
And the go-to tool for this is the Java micro benchmark harness that we
use all the time.
In the OpenJDK, we test all our benchmarking hypotheses with benchmarks written in the JMH tool. It gives you a lot of things for free. You just write your method, annotate it with benchmark. It cooperates these days with the JVM. You have like a black hole implementation, so you just return whatever from the code.
So you properly consume that value.
It's consumed so that the JIT doesn't think that this method doesn't do anything useful and throws away the entire calculation. Instead, you go through a black hole that puts a fence against
Discarding it.
discarding it. It's like, oh, this is going to be used. Yeah, sure.
Yeah.
Then you don't use it, and don't add any much of overhead. So it's a pretty cool thing.
Maybe this is how it looks like.
Benchmarks are simple tests.
Yeah.
Kind of you write
test.
simple Java code. You annotate with various things to.
This benchmark annotation here, and you can add in command line parameters, all that stuff.
There's a lot of cool samples, and the JDK these days we have hundreds, if not more, benchmarks that zoom in on different packages, different utilities, different parts of the system. So we're building that out, cataloging benchmarks.
And the good thing is that people are actually looking at this when we do changes and we do weekly releases, and run all the benchmark. And I want to say to you that they will get back if you did something wrong. They will say that, oh, we have a regression here. What's going on here, guys?
Yeah, that's a little bit of my job description is finding those regressions and run telling to Per's boss. So the results are, we try to look at as many benchmarks as possible over every release, and the result from this benchmark is built into the JDK, so we get the results on every build and look at these. We don't test all the micro benchmarks on every build. That would take too far. But we use this as a way to guide performance work, and then micro benchmarks are a curse and a blessing at the same time. You need to use them as like you would use unit tests in your application stack. They don't tell
every answer.
No, and don't give you the full picture. You can also stare at local optimizations and thing, like you can over optimize something specific, but regress the total system performance. So, but it's a very useful tool to zoom in on things, and we use. We have our own internal visualization tools, but there's also some like this
public tools
that you just dump out the output from the image, and you can.
I think this is nice because you can see the error margin there, and then you can relate that to the actual improvement. So maybe you got this small improvement, but the error margin was like this, and then maybe you shouldn't care too much about it.
Exactly like this.
For example,
not any difference at all between.
And you can, of course, upload this in your favorite, number or Excel sheet and
Google Docs.
Google Docs, yeah.
We have our own internal system, of course, to help us guide and find these things with triaging over many machines and run thousands of benchmarks and everything.
Different columns here are different hardware and operating systems. So you can see a change. Well, how would that appear in that platform, and how will that appear in another platform? Sometimes they contradict.
Yeah. We put some JPEG over here because this is a proprietary system. We can show you this.
Okay, so we come to the next section. Compiler tricks, and this is kind of a thrill or chill section. We're going to go deep now into the inner workings of the compiler.
We're just going to do a cursory glance.
Okay, just a scratch on the surface. But if you think this is hard to understand, bear with us. We will bounce back later on. So this is the circle of life for Java code. We start out at interpreting mod. We'll read each and every byte code. We mutate some state, read the next byte code, mutate the state. And this sounds very slow. And in fact, it is slow, but it's surprisingly fast considering everything that is done.
Right. But we can go faster.
Yeah, we can do that. So what is C1 here?
Yeah, like once we realize that some method is hot enough to warrant us looking deeper at it, we throw it at the first tier of our compiler, Git compiler infrastructure. C1 is that. C1 is originally like the what they call this desktop compiler that was used for the applets. It's a sloppy, the sloppy, quick and dirty compiler. So we use that to generate something that is faster than interpreter, but also has more profiling profiling counters strewn out into the program.
And when we say profiling, we mean gathering statistics about the behavior of the program.
Right. So like which loop is actually executed, which branches.
Which parameters are null, things like what branches are taken, and so on.
So we collect a lot of data on every particular byte executed.
And then finally we can go to C2 after a while, maybe a couple of 10,000 operations or so.
Right, or some other compiler.
Yeah.
Yes. So it's like this tiered approach allows us to get a lot of important data, or that drives assumption, speculation. You can do certain optimistic things if you realize that certain branches are never taken. You realize, you identify code blocks that are never executed and can eliminate them.
And this is the reason why Java sometimes can be faster than other programming languages that are compiled before you run them, because we know more. Not only do we know the code, but we know how the code is run.
Right.
And we can speculate around that.
Exactly.
But sometimes there are unfortunate events.
Right. So even the code, to have the feedback, if you do a lot of speculation, you can de-optimize your code back to the interpreter. So the JVM does a lot of speculation, but puts in safeguards. Like if you're assuming that something is never null, and then you find you trap on something that is not pointing to the null pointer, you get a trap. You roll back your execution and go back to the interpreter. And
we kick back to square. I mean, square zero is the correct name for programmers, not square one.
This is a surprisingly robust thing.
It's the natural course of operation.
Exactly, but it's been a few bugs in this area. But anyway.
Yeah, so let's talk
things that the JITs do to help your program along.
So there is something called inlining, loop unrolling, hoisting, and dead code elimination. There are lots of more, but we don't have time to speak about them today. We have auto-vectorization also. So let's start with this simple code snippet here. We create two arrays, source and destination, and then we copy from the source to the destination. Very common pattern. You see it all the time. And we are running just a loop that iterates over the source length and just, by a segment for segment, copy it into.
Right. But calling methods takes time. So like one of the first simple optimizations that JIT do is inlining. Yes. So you take all the calls, copy whatever is in them into one big super method, and you compile that one instead. This, of course, gets rid of the overhead of many calls, but it also unlocks quite a few other optimizations.
Further down the pipeline.
Like if things that are outside the method that is being compiled you don't know much about, you can speculate too much about it, but everything that is in this big artificial super method, it can do a lot more.
So what you can do, for example, is to do something called unrolling. So every time you do this iteration, you have to check this predicate. I is less than source.length. On every iteration. But of course you can, if you do in chunks of 4, and then you can bump the counter by 4, and then we can just have a cleanup, tail cleanup at the end. Of course we can amortize then the looping by a fair amount.
That this removes 75% of the branches in the main loop.
Exactly, and branching is expensive.
Very expensive, like memory access checks. If so that's one optimization that's bread and butter to what JITs do. Next one is hoisting. Like on the previous slide, on every array check, you would do range checking and such things. If you can hoist that out of the loop, that would be great. So hoisting is the process of taking things that are loop invariant, doing them before or after, or before primarily, so that you don't have to do them. So this now the array accesses are synthetically gotten rid of the array check. Then we are.
And the parenthesis here is this is not pure. This is not Java. It's just to illustrate that this is a
pseudocode.
It's an access without range check. And if you are very, formal here, you will notice that this is not quite equivalent, because if you get an array out of bounds on this line here, for example, the message there will be different. But that will be fixed in the next slide, which is dead code elimination. Because if you look at the creation of the arrays, you can see that this, predicate up here in the if statement will never trigger. So we can just remove that.
Right.
And then we hoisted it and then we removed it. So that's a great win.
So we went from like 3 branches per axis to 0.
0.
So that kind of thing is extremely beneficial in practice. You can go from a few hundred kilobytes to gigabytes per second in throughput in certain cases. The JVM does a lot more. Like we have auto vectorization since early JDK 7, I think. But it's been gradually improved.
So the auto vectorization is that you can work with larger chunks of data. So in this case, we have a byte array, but internally we can say that, well, we would like to look at this byte array as a long array, and then we can do long access instead. And that means that we can, instead of 8 bytes, we can have 64 bytes per chunk. And of course, that will amortize as well, because it's just in one instruction we can work with more data. And so we can see we can bump up 8 steps for it. So it's not only that we can access them in larger chunks, but we need to iterate fewer times.
Right.
But that's not the end.
Right. Long values are 64-bit, and computers these days, they have SIMD registers up to 512 on Intel hardware, probably going to be
even more in the future.
Right. So we have code to automatically, emit SIMD instructions on the processors that support it. Taking advantage of the fact that you don't even have to know if you're going to run on that kind of hardware. The JVM is going to sort it for you, and we can iteratively apply these optimization over and over as compiler does. So we have.
So this is kind of the end game.
Hoisting and unrolling.
Hoisting and unrolling and super wording. So here you can see that we bumped 256 bytes per iteration. So this is really, really high performance. And in fact, these operations here would translate to pure machine code.
Right. Assuming that your inputs are actually large enough to take advantage of this. And that's also... Yeah.
But then again, if it's just a small array, it doesn't matter so much. But if it's a long array, it does matter. So.
Right. But that's something that we pick up during the profiling phases, like how big is your data, and figuring out which
does it pay off?
How deep should we go?
Okay, so let's look at these performance improvements, which is not going to be 13 when I look at my watch. Let's go into those JEPs, because JEPs is one thing. Maybe that's the shopping window of what we're doing, but there's a lot of other things happening underneath. Right. And there is an article written here of all the JEPs that's been, integrated since from 21 to 25, and you can just go there, read all about it. And actually, so these are not some of the deprecations and the removals.
Yeah,
why is it important with the removals and deprecations?
Deprecations, removals, sometimes the key to performance is getting rid of degrees of freedom for your application. If you have code that sometimes goes in and pulls the rug from under your feet, you're always gonna be looking for those exceptional cases.
Yes.
If you can remove things that that sometimes make your program behave in a very different way, then you can simplify and streamline a lot of things.
I remember certainly this one, remove the security manager. That was really a wow moment, because the security manager was all cluttered out in the entire core libraries and creating anonymous classes all the way and really ruining out the startup process.
Right, and surely like we have optimizations in place so that if a security manager is never installed in a system, we realize that at every call site, like I'm going to check if the security manager is on, but it's never on. So we dead code eliminate all that stuff. But still, that's work.
It has to be maintained.
The interpreter has to run through that. It has
Indeed.
to go through all the phases and such. If we can get rid of it, we reduce the resource usage of the JVM.
And there's a whole podcast about deprecation and removals with all our own Dr. Deprecated there. So if you're interested, you can go there.
His name is Stuart Marks.
Yeah. So this one, the first one here, is not about performance at all, but it is a tool to pinpoint performance, snags in your code. So this is kind of a microscope into your application. So now you can say that I want to get notified every time this method is called, and I want to have statistics about it.
Yeah. So JFR has been around now since, well, in some versions since JDK 8. The improvement here in 25 is to get more, low-level method timing and tracing built in. Earlier, you would have to use something like what's it called, either a big profile like VTune, or you could use the async profiler. Still great
This is great
tools
for DevOps kind of people.
Right. Now you can you have that built into your into the JVM on systems with higher granularity than before. So it improves the the insight you can glean from the tool.
So here is an example. I said that I'm interested in hash map resize because I realized that the resize is expensive, and so I get the stack traces of all those, and then I can go in there and maybe see that maybe I want to create my hash map with a bigger upfront size, so I can avoid that kind of thing.
Yeah.
Or you can even trace like class loading and see what classes are loaded, and you can see how long time it takes, and maybe if you can, initialize your class in another thread, or you can try to delay class initialization if you're concerned about
exactly.
that.
Flight recordings are a great tool now. Now they are better than ever. We still, there's still the mission control application to consume them in a visual fashion. This JFR view tools are, command line complement that I find very, very nice to use, since it weaves easily into tools and benchmark tools.
Yeah. So how about this one? This is kind of complicated.
Oh,
can you tell us more about it?
I like this one because there's an anecdote about the ZGC project, finding that the way that we put in. So whenever you do memory accesses or accessing a reference object in Java, you need to have a cooperative barrier for the garbage collector, since objects are prone to move around.
Yeah.
So you can you allocate something in one area, and then during the
it's like a 3-year-old child running around.
Yeah, you have something else running around, rearranging your blocks. So to avoid stepping on Lego, we have barriers to make sure that if I'm accessing a reference to an object that has moved, you patch it up a little bit, and then go and look at in the right place. So this was done in the parsing phase when doing parsing the code. At
compilation.
At compilation, yeah. So it was done very early in the JIT phase up until
recently
JDK 24 for G1. So it was a little bit differently for different GCs. ZGC was earlier in doing the late barrier expansion optimization. So, but really, what it entails is, rather than doing all the barrier stuff up front in the parser that created nodes in the compiler graph tree to be compiled, it meant that the compilations were growing quite large. As you inline more and more stuff. You have barriers, accesses to objects all over the place. Every such access, adds barrier nodes to the compiler tree. Long story short, if we can move them to the backend, not have them as part of the sea of nodes graph tree that the optimizing compiler is operating on, that reduces the problem of compiling quite substantially. So this is good
for cloud application, for example.
Yeah, it reduces the resource usage is in part of the story for why we see quite substantial reduction in memory use. Is that we by doing this we reduce pause times.
Yeah.
There's a flip side of this. This was originally done in the ZGC, not so much as a warm-up startup optimization, but in the scope of ZGC, the original case was causing correctness issues. So this was originally correctness issues that realized that no, if we apply this everywhere else, we have a big startup improvement and possibly better correctness.
Okay, so this one reduces the possibility of starvation of the garbage collector. We will skip that because we have more interesting stuff. So here we have a ZGC generational mode by default. And what does it mean by generational? Well, first, the ZGC is for larger heaps in terabytes, and it was introduced in 2015, and gradually we moved to this generational stuff. And before, we had non-generational mode, meaning that the heap was just one single blob. And when we created a new object there, like this chicken here, which is short-lived, unfortunately, and then the hens, they will live longer. And the geese will have to look at all these objects all the time when it evaluates whether they are alive or not. So if we look at the time distribution, as I said, most objects die young.
Yeah.
And that's the hard reality.
Generational hypothesis.
Yeah.
It's been around since in academia since the 60s, and most other garbage collectors said GC was already generational.
And the idea is to have a separate place for all the chickens, so we get created here. And of course, if you look at them both at the same time, the distribution will remain the same. But if we look at them individually, then because the objects move to the other one, they have to die in the sense that they are moved or either survive. So the probability that they will die will relatively increase, whereas it's been the other way around. It's like me. I have now lived for like almost 60 years,
right.
but I haven't died.
No.
So that means I have get rid of all those probability when I drove a motorcycle or whatever I did when I was a crazy kid. That's all gone away.
Yeah,
so I will probably live longer than the average guy now.
Right. Expected life expectancy increases as you get older, which is the same for objects.
Yeah. So therefore, it's likely we spend more time there with the kind of kids and spend less time here, and that means that the garbage collector is more effective. So that's the statistics. What's this one?
Complete object headers. So we're running a bit short on time, but complete object headers implemented by Roman Kenke. So this was an external contribution. Is now in 25 not enabled by default, but it's not out of experimental. It allows us for so objects all carry some luggage. We call them object headers that has information like bits pointing to which. Which class is this object of? We have some space for hash codes. We have space for GC specific bits and locking and a few other things. And in total on a typical 64-bit JVM, this adds up to 12 bytes I think, per object, which is quite a bit of overhead. It's like on an integer box object, which carries 4 bytes of useful data.
That's a lot of overhead.
That's a lot of overhead, yeah. If you could reduce that just a little bit, then that would be great. So complete object headers in this iteration that is now in JDK 25 reduces typical object size from 96 to 64 bits, so saving 4 bytes per object. Yeah. That's 4 bytes per object adds up to quite a lot of improvement.
If we look at how modern CPUs looks like, it's very important that we, stack more things into the caches for performance reasons.
Yeah, you mentioned earlier that like the retrieval stuff, 110 cycles on a typical CPU to retrieve from memory, but execute, calculating. So compactness is important for.
So that moves up a lot of. We get more space in L1, which we can move objects from L2 to L1 and so on.
Exactly.
And an ever increasing amount of stuff can go further up this tower, so to speak.
Exactly. Getting rid of excess space is one of the main things I think for the future for JVM improvements. This particular feature, can improve JBP15 by, 22% less heap, 8% less CPU. It's a great thing. It's not enabled by default, but you should really run your applications with it.
You can try today with this switch down here combine.
Usually, all features comes with trade-offs. The only known trade-off with this one is that it limits the number of classes you can have in your application to 4 million.
It's very unlikely that you will have that ever. But I mean, let us know if you have more than 4 million classes, and I will, tell my friends, colleagues.
Then you can just turn it off, and you can run with your 4 billion or something limit as before.
Okay, so we have 5 minutes left. I think we can stop here and maybe see if they have any questions.
Right, if there is anything particularly of interest to anyone. We have some slides on Leiden, which is the startup
effort,
big startup effort of the Open JDK team.
But any questions? Okay, let's talk about Leiden then. Good.
So there are new language features that are being released. We were just at the Brian Coates. Some of us were at Brian Coates.
Yeah.
Are there any language features that negatively impact performance, or have you seen this JDK?
So the question is, with the introduction of new language features, are there any performance regression? And I think the answer is yes. We need to keep tab on them, and of course we are trying to mitigate that before we launch the thing, whatever it is.
Right, and that's one of the reasons why we have to focus so much on our micro benchmarks, because like many of these system benchmarks, especially maybe 2015, likely won't be affected by any new language features, because the benchmark is set in stone 10 years ago. So we have to create new benchmarks stressing new language features all the time. That's a big part of designing.
But I think that's one part of the unglorious job we have to do to kind of clean up all these regressions, or all these regressions, but some of the regressions that gets introduced, like
before they become a problem.
Before they become a problem, exactly. So that's a good question.
Very good.
Anyone more?
So do you see any other kind of big change in Java's future other than Valhalla that has like a huge impact on performance?
Yes. We are working on a lot of things, and we think I have something on another slide here, which we haven't talked about, but that allows you to, that's called lazy constant, for example, allows you to say that this is a constant, but I want to compute it later on. But when it's computed, I want to treat it as a constant, and it may be something called constant folded by a VM.
Right.
And that is just the first step, so we have more things up in our sleeves.
I would make a short shout out to the foreign function memory stuff as well, Panama, which already is out there, but it's, we're working on lots of improvements in tooling to make it easier to integrate JVM with native binaries and such, which is very useful.
Yes. Okay.
Is it the last time to get excited about the GC or Shenhua, or are we still stuck with our sponsor, Azul?
So what's the question? Can you repeat?
I couldn't really catch the question, sorry.
I'm trying to say, in previous versions in Java 21, etc., we tried to experiment with ZGC and Shenhua garbage collectors, and for really big heaps, so unfortunately our heaps are really big, and we are stuck with Azul's JVM, unfortunately. So now is it at last the time to get excited to try out ZGC with
So the question, as I see it here, is that will the ZGC be able to handle extreme heap sizes? And the answer is that I know that they are working on ZGC all the time.
Right.
But I'm not, I'm not into that detail of exactly what's being worked on there. But I think you can have,
I don't have any comparative, I don't do comparative benchmarking with other vendors, but I do know that with the new iteration of generational ZGC, you will see a leap in performance on many applications. So it's a good time to, I think, retry. Yeah.
Okay, so that's great. So let's just...
Yeah, we're running out of time here, but...
That's great, because we had
a
lot of questions. So.
Anyone else for our last?
Okay, one last question.
Could you just mention a few notes about the Leiden and startup?
Okay, Yeah, a lot. So question is, can we tell a little bit more about laden? And yes, we can. So the objective with laden is that you can do a training run. And when you do a training run, you can store all those class initialization, maybe some profile data and even code in something called an AOT cache. And then when you start up, you can just load that AOT cache and off you go. So you can skip all this sequence of the circle of life for code, and you can just start there. And that means faster startup and better warm-up time.
Right.
So that's the gist of Laden.
So the promise of Laden is to have no added limitations. Like it's Java as ordinary, but you have this AOT cache to speed it up on first.
And it all
warm-up.
relies on speculation. So if you speculate and then deploy it, and the speculation doesn't hold, okay, then you just go back.
You can get a little bit of
it's a
regression
fail-safe
if your
mechanism.
training run and misses the target. That's always but
Okay.
it's a very promising technology. It's going to improve. Work that is being done for future releases is to do AOT compilation entirely into your AOT cache. You can tune how far you want to go and how much you want to put in that.
Okay, so I think we're going to get kicked off
Yeah.
of the scene.
Thanks.
So we have to stop. But thank you for your interest.